Alors, vous, là, les techniciens qui s'occupent de l'arrangement en ligne, c'est bon? La personne est prête? Alors, on va passer à la présentation suivante. Merci, monsieur Rakutunzanar, pour cette intervention. Vous pouvez regagner donc votre place. Maintenant, si la personne qui va présenter prochainement est prête, on va le faire entrer. Hein? Okay, good morning, sir.
Hello. Hello.
Okay. If
Can you hear me?
So do you hear me very well?
Yes.
Okay. So we have here a presenter online. He is Dr. Emanuele Locatelli from the University of Padova, Italy. He will present us the following subject: adsorption properties of polymeric brushes. Let me say some few words on the biography of Dr. Emanuele Locatelli. He is at the University of Padua, and he contributes to nanotechnology through soft matter physics. His works include studying the condensation of DNA nanostructure, DNA nanostars, and the shape control of patchy nanoparticles under confinement. A significant part of his research uses simulation and scaling theory to study polymer brushes able to adsorb colloidal-like solutes. In equilibrium, he observes a phenomenon where the brush collapse followed by successive reswelling as the amount of solute increases. This dynamic is rationalized through a scaling theory where adsorption is seen as a progressive worsening of the solvent conditions. This is just a very short biography of our presenter. So now I'm going to give him the floor. You have the floor, sir. Hello, do you hear me?
Okay. Now I hear you. Now I hear you.
Okay, you have the floor.
Okay, thank you very much. Thank you for the very kind introduction. I'm Emanuele. I work at the University of Padua, and I present now, as the chair said, a numerical and theoretical study on the absorption properties of polymeric brushes. This work was founded by the Ministry of University in Italy, and so you see all these banners, and was performed by a PhD student, Clemens Franz Forsman, who graduated early this year. And the content of this work, of this presentation, are in this paper, published on nanoscale advances, which is, you can see it here. Now, we are interested in the problem of the absorption of particles by polymeric brushes because of the general problem of water pollution. And in fact, it is now well grounded, proved that fresh water is not an unlimited resource, And in fact, there are plenty of regions in Africa, for example, but also in Asia and in the Americas, where freshwater availability is very scarce throughout the year. As you can see from this map, all these red zones are indeed regions where water is scarce, fresh water is scarce throughout the year. Fresh water means water that you can drink. And if you actually, this is you could think that water is actually very abundant, but the vast majority of water is indeed in the oceans and in the sea, so it's salty water that you cannot drink. And the vast majority of fresh water is actually essentially trapped as groundwater, and it's not so accessible for our use, especially in certain regions. And in particular, on the other side, what is the main, let's say, usage for fresh water are agriculture and industrial. What people use in municipality consumption is very limited. And in particular, if you see the water consumption for agriculture is large, but is also large what is agricultural drainage, so what you get, let's say, is lost in agriculture, which could be, in principle, also recovered if we are able to clean it. And in the end, of course, the problem is much present, because in the future there will be an increase of freshwater demand because of still ongoing population growth, and also because of economical growth. And so population growth will bring an increase in agricultural demand, and economical growth will mean essentially an increase in industrial demand. And this essentially will lead to a decrease in freshwater availability, because of course water resources will become less and less available, and also because of pollution from agriculture and industry, and in general because of global warming, which, as you know, it's changing also the weather, and so with it our ability to rely on freshwater, a freshwater cycle, reliable freshwater cycle. And in fact, it is forecasted that nearly 6 billion people will suffer from clean water scarcity by 2050, if everything goes as is going now. And so we need technologies that can help clean water from harmful substances. And indeed, the nanotechnology could present it themselves as very useful and impactful technologies in this respect. Why? Because as we will see, there are now many techniques. Some have drawbacks, and in particular, most of them, of the current techniques, do not address the problem of nano pollution. And so our idea was to consider nano-functionalized, let's say, smart materials, which macroscopically will look like this sponge-like membrane that you can see here from a TEM image that some collaborator sent us. And in this material you have pores with a distribution of from nano to micrometer size, and these pores are the ones that in principle are going to be coated with polymers. And then our idea is to study how these polymers that coat these pores are able to capture the pollutants by means of adsorption. Another approach could be to have nanoparticles like these star polymers, in which you have polymers grafted again on a core, which in this case is spherical, like in this image. And then you can play with, for example, the chemistry of the material, or you can imagine to play with the architecture itself or other polymeric properties to maximize absorption. This is, in general, our idea, the idea of our research. Polymers, for those who perhaps don't know them, are objects that are also known as macromolecules. So they are molecules, big molecules, composed of many repeating units that we call them monomers, whatever they are. For example, polypropylene is a polymer, and it's formed as a chain formed by propylene molecules. DNA is a polymer, and it's formed by nucleic acids, bases. Proteins are polymers composed by amino acids, etc. And the strong points of the polymers is the fact that they can attain very different properties because of the fact that this assembly can be guided and can take place, can be arranged in many different architectures. So here you see a linear polymer, here you see a ring polymer, a star polymer, as the one I showed before, etc. etc. This is like a bottle brush, and these are dendrimers. There is a whole zoology, and we are particularly interested in grafted polymers, so where one of the ends of a linear chain is attached to a surface. And in particular, if let's say one is more interested to the chemistry, the material called poly-2-oxazolene presents itself as a possible monomeric unit for polymers that have been can absorb material or pollutants at the nanoscale. These pollutants, for example, are heavy metal ions. Let's say the other big advantage of this material is the fact that they can be considered as smart. So that they can be controlled externally by some stimuli such as temperature, pH change, light, possibly, etc. So you can play with the chemistry of the polymers to achieve this. And the main ingredient, let's say, for if we want things at the temperature, for example, is the so-called coil-to-globule transition, where a polymer can be, let's say, extended, so in the so-called coil state, at low temperature or high temperature. There is also this picture, and then by lowering or increasing the temperature, then you go into the collapse state. And this is the equivalent for brushes. The use of polymers for water treatment has been already known. That there is, for example, a recent review. What we were more interested, as I already mentioned, is to play with the polymeric properties to give a theoretical understanding of how different architecture, and this is just part of course, of this very broad picture, this presentation, can affect the absorption properties. Another idea, another selling point for a smart material made of polymers is the fact that you can think of make this material selective. So, for example, imagine that you have water that has both lead and magnesium in it. So magnesium you want in general to keep, but lead you don't want because it's poisonous for us. And so you can imagine to have a material that you can design to absorb selectively just the lead and leave the magnesium there. And by pairing this selectivity with the smart properties that we see in the previous slide, you can think of capturing these ions and then retrieve them, for example, in a sort of paradigm for a circular economy, when you retrieve your waste. And so, as I mentioned, there are many different, let's say, techniques for water remediation, as called, but most of them rely on chemistry and on macroscopic, let's say, a macroscopic kind of filtration technique. For example, this one, the one with sand, which is used usually also in conventional, also in here in conventional plants for retrieval of wastewater. But of course, you know, I already said what are the advantages with respect to these methods. The fact that you can effectively remove also nano waste from the water. You can do it selectively, and you don't need any chemicals. On the cons, of course, there are high investment costs, at least at the beginning, and so this is probably going to, this technology is going to be developed in a number of years, and it will become probably affordable for everyone, hopefully. Now, from our perspective of our research, a membrane is not this object here that you can see here, you see in the picture. So we don't, we are not able to simulate in a great detail a whole array of these nanopores. But what we do is to focus on a single nanopore. And we consider the detail of the nanopore being coated with polymers, okay? And so we will have two relevant length scales here. One is the, what is called the height of the brush, and the other is the length or the size of the pore itself. And in this research, we are in the limit where the height of the chain is not is quite smaller than the diameter of the brush, so that we will simplify this kind of cylindrical or circular geometry with a planar one. As in all the brushes, the controlling parameters are the number of monomers per chain, which tells us essentially how high the brush can be, and the so-called grafting density, which is the number of chains over the unit area. Okay, so the more chains you have on the unit area, the more this will impact the properties of the brush. And of course, just a very quick summary of the quantities we will be interested in. When you have a polymer, you are interested in its gyration radius, which is essentially how the material, the polymer, is organized around the center of mass, and which has this formula. And in particular, as I already mentioned, the polymers can have good solvent and poor solvent condition behavior. And in good solvent, the polymer likes the solvent, so the polymer is in a coiled state and is quite kind of stretched, and its gyration radius grows with the size of the polymer with a certain universal exponent. Whereas in poor solvent, the polymer doesn't like the solvent, and so it wraps on itself so that the exposed surface is minimal. And so, since the minimal exposed surface is the one of a sphere, then the polymer compactifies, and now its gyration radius scale with this other exponent, which is also universal. Okay. For a brush, what we are, as I said, the grafting density will impact the behavior of the brush, because you can think it as in this picture that if your polymers are very close to each other, they will start feeling each other, and so they will stretch because there will be no space to stay close to the surface. And so you will have that, I mean, it is possible to calculate in the so-called scaling regime the height of the brush as a function of the grafting density itself and of the length of the polymer. And as you can see, the height of the brush, by this formula, the height of the brush is linear in the length of the polymer, and has this particular scaling exponent with respect to the grafting density. So this to say that we are going to consider long polymers because we assume that chemists are able to create this polymer and graft them on a surface. And so we will always consider polymers in this so-called brush regime where they have this scaling. Otherwise, they have different scaling. Okay? And in particular, so this is also called the Alexander-Dejean model, and in particular, this model predicts that the concentration of monomers, let's say as a function of the distance with the surface, is constant, and then drops when at the top of the brush. So this will be the height of the brush. Okay. In reality, one sees that this profile is parabolic, not really a step function, but nevertheless, and this we will see in our simulation, but nevertheless, this is a bit the picture that you can see here. Polymers are stretching and they are extending out because of the presence of the other chains. And so this I have already said, and so just to say that we will be in this region of this kind of scaling plot. Now, what we do is to consider a coarse-grained model. So I already told you that one can have different monomers, whatever, but if you want to establish a universal or kind of a broad result, you need to consider, to take away the details, and so we will consider this kind of more coarse description where the different monomers are interacting via a sort of paradigmatic interaction potentials, such as the Lennard-Jones potential that I hope you already know. And the idea is that monomer do not have any chemical attraction to other monomers, so they like the solvent. And but the chemistry of the monomer is such that there is an interaction between the monomer and the colloid, and so colloids will be kind of trapped when they come close enough to the brush. And this is how adsorption happens in our model. And we say that the characteristic strength of the adsorption with respect to the thermal energy is given by a parameter that we call epsilon. Another. So what we do, and this is a couple of videos, we have our brush and we let it absorb a certain number of monomers that are in suspension above it, and then we see what happens to the brush itself. When equilibration happens, when basically we don't see any more change in the properties of the brush, and for here, for example, is an example of a few colloids, of a few pollutants that have been trapped and then have traveled in the region where there is the greatest brush density. Okay. So one first result is that we can see how colloids modify the brush, and in particular we see it in the density profile that I've shown you before. So if I have very few colloids, nothing happens. Then if I start adding colloids, things start to happen, and you can see that at first the profile is not really very much modified, but the colloids that you see here in this orange line start to accumulate at the bottom, And then what happens is that the brush starts to be modified and it starts to collapse. Okay, and in the end the brush is completely collapsed, and but it's depending on this parameter epsilon, its absorbing power is not completely spent, and it can keep absorbing and reswell. This is something that has been observed also in experiments, other kinds of experiments that were done in the past, but indeed that's the correct phenomenology that you expect in this case. So I just sketched the theoretical approach that I also mentioned in the introduction, and the idea is that we consider a portion of, this is like an approach that is inspired by blob theory, so the theory by which you can regroup monomers into effective units. And essentially you can regroup both monomers and pollutants into effective new elements that are not in good solvent but in poor solvent. And so you can replace your mixed system via let's say, single polymeric system in which you don't have an homopolymer, which means that all the monomers are equal, but you have a D block of polymer. So a polymer in which one part is of one type of monomer, and another type is another type of monomer. In particular, this for us means that one part is in good solvent and one part is in poor solvent. It's in poor solvent because there is an effective, so there is an attraction, there is an energetic gain for the ions to be absorbed on the monomers, and so the monomers will start grouping and collecting around the pollutant particles. And so by effectively they will become the polymeric material will become more compact and it will look like as it is in poor solvent. And then one can do a blob argument and in the scaling limit renormalize the brush into what is called an Alexandre Dejean equivalent brush of blobs, in which you sort of mediate the properties between the good and the poor solvent. And okay, I don't annoy you with the technical details, but the point is that this provides us with a way to get an analytical expression in the scaling limit for the height of the brush as a function of the pollutant material that has been absorbed. And so this is the result, a comparison between the theory and the simulation. You need to sort of do a series of assumptions that I will not detail here, but you see that our theory, which is this orange line, fits the data very well. Let's say the main ingredient is to get the amount of colloid that are recruited around each pollutant particle, which is a decreasing function because of course monomers will be sort of started to be shared, and so you cannot have a fixed number of monomers.
Please, Doctor.
And
please, Dr.
Point,
please, can you hear me?
The brush will be completely collapsed, and so you will,
excuse me, can you hear me?
More aggressive.
Can you hear me, please?
But so, let's say the comparison between the theory and the simulations is very favorable, and it allowed us to also to perform to get a master curve, which is similar to what holds for I'm almost done.
Excuse me, Dr. Locatelli. Could you finish within 3 minutes, please, because you have out of your time.
I'm almost done, sorry. So I will give a master curve that is similar to what you have in good solvent. And so, again, with this I conclude. These are measures that can be done also experimentally. And also they have been seen similar